Hey, do you know what this is? This is a high voltage electric distribution switch. Your local utility uses these to distribute power throughout your neighborhood. These things are everywhere. Here's another one. Let me show you how these things are used. This is a basic electrical schematic of the switches that we just looked at out in the field. Electric utility switches are usually divided into compartments, also known as ways. In this case, way 1, way 2, way 3, and way 4 make up this four-way switch. Each compartment contains an individual switch, also known as a switchway, and each of the four switchways are connected together by a copper bus bar inside the cabinet. When high voltage switches are opened under high loads, it's not uncommon for arcing to occur. So in order to minimize the hazard of arcing, the switch contacts inside the cabinet are enclosed within a sealed enclosure. In older switches, this enclosure was filled with oil or sometimes a gas. The oil or gas was used to suppress the formation of an arc when the switch is open. Some of the newer switches are air brake switches in the sense that there's no arc suppression medium inside the cabinet. These switches tend to be a lot larger than oil or gas switches. The newest switches are vacuum switches. The electrical contacts in a vacuum switch are contained in a low pressure vacuum housing in which all of the atmospheric gas has been removed, leaving no medium of any kind in which an arc can actually form. When the switch is installed by the electric utility, high voltage distribution cables are connected to the switch, which are in turn connected to the utility's substation. This is the power source for the switch. In this example, the source is connected to way 1, and when way 1 is closed, the copper bus bar becomes energized. Additional cables are connected to each of the remaining ways, and typically they're branched in different directions. This is how an electric utility bifurcates, or in this case, trifurcates a single circuit into multiple branches. This is also why you often see switches located near intersections. The individual branches typically follow the roadway in multiple directions to provide power to the entire neighborhood. Each of the individual switchways are then closed by a line worker, and each of the individual branches then become energized. Let's look at a switch that's actually connected to a distribution circuit. Here we have a very simple electric distribution circuit shown in yellow with two four-way switches connected to it. We'll just refer to this yellow circuit as circuit Y1 for now. As I mentioned earlier, all distribution circuits originate at a substation, and most substations can support multiple distribution circuits. The first run of cable exiting the substation is usually referred to as the substation getaway. And downstream of the substation, the getaway is connected to the first switch where the circuit is bifurcated into two separate branches. The first branch provides power to a residential community. The circuit then continues downstream and is connected to a second switch where it's bifurcated again. One of the branches provides power to an industrial center, and the second branch to a hospital. One of the most useful applications of a switch occurs when the utility needs to perform work on the distribution system. If maintenance or new construction requires the circuit to be de-energized, the utility doesn't actually have to de-energize the entire circuit. A line worker can just open the switchway connected to the branch under construction and de-energize that portion only. In this example, this allows for the factory and the hospital to continue receiving power. When the work is done, they can simply reclose the switch and re-energize the branch that was under construction. Some newer switches are also equipped with a function called auto-sectionalizing, which is shown on the second switch on the right with the letter A. In the event of a fault on the system, say one caused by a vehicle accident, current sensors installed within the switch cabinet can detect the fault current on the affected branch and automatically open the related switch. This not only protects the public and the first responders, auto-sectionalizing allows the hospital and the residential community to remain unaffected by the accident and continue receiving power. Now, what if the vehicle accident occurred on this portion of the circuit? Opening the switch upstream from the accident will de-energize the affected portion of the circuit, but it would also cause the factory and the hospital to lose power. This is where a circuit tie becomes useful. A switch becomes a tie switch when it contains two separate power sources from two separate circuits. The switch on the right is usually powered by circuit Y1 connected to the first switchway, which is currently de-energized due to the accident. The tie switch, however, has a second power source provided by the circuit in red. We'll call this R1. R1 is connected to the second switchway. Notice that switchway number 2 is normally open, since circuit R1 is not the primary power source for this switch. It's only available as a backup source. Since this is a tie switch with a backup power source, a line worker can open way 1 to isolate the area of the circuit where the accident occurred. They can then close way 2 and re-energize the factory and the hospital using circuit R1. When the accident is cleared and everything is repaired, everything can return to its normal state. Before we go, let's take a look inside of one of these real quick. This is a 4-way vacuum switch. You can see here, starting from the left, we have way 1, 2, 3, and way 4. Each set of 3-phase distribution feeder cables are connected to the switch bushings labeled A phase, B phase, and C phase. Way 1 in this switch appears to be empty since no cables are actually attached to these bushings. You can clearly see the cables connected to way 2 coming up from the underground conduit system, as well as way 3 and 4. The switch levers that open and close each of the switches are located right here, one for each way. The little glass windows at the bottom enable a line worker to look inside the cabinet and actually see the switch contacts to ensure that they're in the desired position. This is called visible disconnects and is a safety feature for line workers who are operating the switch. The little white boxes attached to the cables on way 2 and 4 are part of a fault indicator system. The boxes are current sensors that monitor the electrical current in each cable. If a fault occurs, these sensors detect the sudden increase in current and trigger a little red flag to pop up in the glass window at the top of the switch cabinet. This helps line workers detect the location of a fault without actually needing to open the cabinet. Once the fault is cleared, the indicator flag will be reset for next time. Now let's close this thing up and get back to work. Pretty cool, huh? Now you know. Thanks for watching.